remember before we had a symmetrical load, so we could assume these were just 1/2 of that loading, but we can't do that now because, well, AY and BY are going to be different values. That means this time we actually have to take a moment around a specific point. So I'm going to do the sum of all moments around point A, and the way to write that is this. Sum of all moments around point A should be 0. So what that means is if I add up all the rotations around this point, it should be 0 because this beam can't be rotating, right? It should be in static equilibrium. And so what are all the rotations caused by? Well, first I think I need a little bit more information. Where is this 8,000 pound load? For this problem, why don't we say it is 17 feet from the left side, and that means there's 3 feet between here and here. So now that we have an exact position for this load, we're going to say that this 8,000 pound force is causing a rotation around point A, and it is 17 feet away. So it's going to be 8,000 pounds times 17 feet, and that gives you the moment around point A caused by this force. The other moment is caused by this distributed load, and so that is 1,200 pounds, so plus 1,200 pounds per foot times 20 feet, right? And so when I do this 1,200 times 20, that gives me the total force provided or caused by all of this distributed load. And where is that load acting? Well, it's everywhere, but you can actually model all of that force as a single point load that's acting in the center of the beam. So when you're dealing with distributed loads, technically there's no difference in terms of rotation between all of this load being spread out or concentrating the entire load halfway across the beam. Either way, it gives you the same moment around these two edges. So we're going to say, we're going to pretend all that force is acting 10 feet away from point A, so that distance is going to be 10 feet. So we have two moments, right? The force times the distance due to this force, and the force times its distance due to the distributed load. And that's what I have here. There's also one more force causing a moment, and that's By. It's going to cause a counterclockwise moment around point A. And so I'm just going to make counterclockwise the negative direction. Typically people make that the positive direction, but it doesn't really matter as long as you're consistent. So I'm going to say minus By times its distance away from point A, which is 20 feet. And so we have 1, 2, 3 different moment terms. All of that summed together should equal to 0. So now we're just going to do some algebra here. So we have 8,000 times 17. Let's plug that in the calculator. That gives us 136,000 for the first term. And then we have 1,200 times 20 times 10. So we're going to do 1,200 times 20 times 10. That gives us 240,000 for our next term, so plus 240,000. And then minus 20 By. Let's go ahead and move that to the other side of the equation. So we're going to say equals 20 By. So now that becomes a positive term. 136,000 plus 240, that's 376,000. Is equal to 20 By. Final step, divide both sides by 20, and that gives us By is equal to, let's plug it in, 376,000 divided by 20. That gives us 18,800 pounds.